welcome again to Science in 5. We're continuing with the revision of the trial paper, the mock trial paper that we've got. So we're on question 5. It's about work, energy, and power. A truck of mass 15,000 kilograms traveling at 54 kilometers per hour approaches a rough decline of length 1,200 meters and vertical height 800 meters. The driver applies the brake so that the truck descends at a constant speed of 54 kilometers per hour from point A to point B. Assume that the engine does zero work. So 5.1, the definition, they're giving us a clue as to what we can use to solve this problem. We want the work energy theorem. So the work energy theorem is basically that formula that says W net equals W net is equal to delta EK. So in words, you would say the work done by the net force is equal to the change in kinetic energy. Okay, so we just say the work done by the net force is equal to the change in kinetic energy. Okay. All right. So that's what 5.1 is. So just remember that trick. Don't just say formulas are in the formula sheet and you don't spend time learning them. It's very important that even though the formulas are in a formula sheet, you take time to understand them, how they work, and actually to deliberately want to know the formulas. 5.2, so I'm going to be working with this space, right and rub. What is meant by the term non-conservative force? Now guys, there's one of our videos, apparently that's doing well. We speak of 3 ways of calculating the work done by a gravitational force. So basically, if you look at how a gravitational force operates and the work done, when you move between 2 points, you'll appreciate this idea of what a conservative force is, or non-conservative force. Okay, so basically non-conservative force, we are saying it's a force which does work that is dependent on the path taken. So in other words, if you take a longer path, you will do more work with this kind of force. Take a shorter path, you will do less work. The opposite of a non-conservative force would be a conservative force, like your field forces. So conservative forces are your field forces. The work done by a field force does not depend on the path or the route that you take. Okay. And then 5.3 says, write down the non-conservative force that acts on the truck as it descends. So the non-conservative force that acts on the truck as it descends is the frictional force. So friction is an example of external force. It's also viewed as a non-conservative force. So the presence of friction means the mechanical energy of a system is depleted. That is why a swinging pendulum will eventually come to rest, because there's a non-conservative force that acts on it. 5.4 says, using energy principles only, determine the average frictional force that acts on the truck as it travels from point A to point B. So energy principles that we can use, or we can think of, work energy theorem. I think this is the one that we can use. That's why the question even said, use the work, state the work energy theorem. Or we could use the idea that the work done by the non-conservative forces is equal to the change in kinetic energy. Or we could also say, well, the mechanical energy in an isolated system is conserved, but if there is an external force, then the Emec initial plus the work done by that force should be equal to the Emec final. So I think we will let's start with this one, the work energy theorem, and then we'll look at how each one of these formulas are actually the same in terms of the algebra involved. Okay? All right, let's go for the work energy theorem. The work energy theorem says work done by the net force is equal to delta EK. Can we identify the forces that are acting on this object? If you can identify the forces, then you can easily calculate the work. So what are the forces? Well, the first one is the gravitational force. The other one, the normal force, though it will do zero work. Why does the normal force do zero work? It acts perpendicular to the direction of motion. It has a zero component in that direction. And then the force opposing motion, the frictional force. Then we also have the components of the weight. We have Fg perpendicular and we have Fg parallel. The component of the weight parallel to the surface. Fg perpendicular, the component of the weight perpendicular to the surface. So in terms of the net work done, we said this force does zero work. So we are looking at the force of gravity and the force of friction. We have been told clearly that the engine force does zero work. Okay. Now, so we're going to say W net is equal to delta EK. Right? Work done by the gravitational force plus work done by friction is equal to, we are also told an important clue in the question, constant speed. In a straight line, constant speed means change in velocity is zero, acceleration is also zero, the net force is also zero. You can even add and say the change in momentum is also zero. The change in the kinetic energy is also zero. Okay. Now, let's work out the work done by the gravitational force. Again, we say there are three ways of working out the gravitational force. Two of the ways focus on the movement along the incline. Two of the ways focus on the movement that happens when the object moves along the incline, and we look at the forces that are acting on the object as it moves along the incline, and the other option looks at the object as it moves vertically downwards. So let's say this is the object represented by this big dot. As it moves down the incline, there is Fg parallel, the component of gravity pulling the object down. And since the object moves from A to B, we say it moves a distance of 1,200. So we can say the work done by gravity is Fg parallel times the distance times the cos of theta. Work formula: force, distance, cos theta. And the direction of motion is always taken as the 0 degree direction. Take the direction of motion as the 0 degree direction. Measure all angles anti-clockwise. That's fine. That's fine. So, what is Fg parallel? Well, components are either cos or sine. So in this case, Fg parallel is mg times the sine of theta. Right? Now, do we really have to calculate this angle theta? Because we want the sine of theta. Yes, you could calculate that, that's fine. But you probably don't need to calculate, because we know that the sine of an angle means the ratio of what? Opposite over hypotenuse. If this is my theta, this is my opposite side, this is my hypotenuse side, the ratio is 800 over 1200. That's what sine of theta means. Okay, so I can actually say it's, what is the mass of the truck is 15,000 times 9,8 times the sine of theta is the ratio of 800 over 1200 times the 1200 distance. The cos of 0 will give me 1. Okay, so if I feed all this into the calculator, if I say $15,000 times 9.8 times 800 over 1200 times 1200, it's giving me 1,176 times 10 to the power of 8, that is now joules. So that is the work done by the force of gravity, taking this approach. Okay, alternatively, I can say, well, since I know the vertical height, I'm going to consider the object, this truck, is just moving this vertical height of 800. In this case, the force that acts vertically downward is Fg. So if I take this approach where I consider the vertical height only, I can say work done by gravity is the same as the change in potential energy. Since we are going in the same direction as motion, there is actually going to be a positive change in potential energy. Or we can say this is EP times the cos of theta. Again, the theta will be 0. So this cos of 0 makes this whole equation become 1. Cos of 0 is 1. What is EP? It's mgh. What is mgh? It's the 15,000 times 9,8 times 800. It will give me the same answer, 1,176 times 10 to the power 8 joules of energy. So now I know what the work done by gravity is. Okay, so I come back and I say 1,176 times 10 to the power of 8 plus work done by friction equals 0. Therefore, I can say work done by friction is negative 1,176 times 10 to the power 8. Okay. Now let's go to the frictional force, because the question says the average frictional force. So we know that the work done by friction is actually the frictional force times the distance times the cos of 180. Why? Because again, going down is the 0 direction of motion. Friction is acting anti-parallel to the motion, so it's 180 degrees. So the work done is negative 1,176 times 10 to the power of 8 is equal to the frictional force times 1,200 times the cos of 180. We get a frictional force of 9,8 times 10 to the power of 4 newtons. So we have to note that in this case, the frictional force is a combination of the braking force and the surface friction. But we're not going to go into that. Okay. So, and it's in the opposite direction of motion. So it's up the incline. So we get a frictional force of 9,8 times 10 to the power of 4 newtons. All right. Now, we could also use the idea of the work done by the non-conservative force equal to the change in mechanical energy. Okay, but if you look at this formula, it basically boils down to the same that we've done. Work done by friction is equal to 0. How so? Well, the non-conservative force we've identified is the frictional force. Okay, so let me create space here quickly. So we already know what a non-conservative force is. Okay, so a non-conservative force, for example, friction, the longer friction acts on an object, the more work done that is frictional, the more energy that will be lost to the force of friction. So this means we are saying work done by friction is equal to change in mechanical energy. Mechanical energy is the sum of EK plus EP, which is the delta EK plus delta EP. All right. But we've just said since the speed of the object is naught, I mean, it's moving at a constant speed, not that the speed is 0, but this object is moving at a constant speed in a straight line. It means there will be no change in kinetic energy. So this formula simplifies to work done by friction is equal to delta EP. Delta EP is the same as the work done by the gravitational force. So this leads us again to this idea that since we know that the work done by the gravitational force is 1,176 times 10 to the power 8, we will get the same work done by friction. And then we'll get the same frictional force. So this and the work energy theorem idea are congruent. So for practice, you can actually carry on with this technique and see whether it will give us the same idea. Okay. Then the other one is about mechanical energy. We say Emec initial plus work friction equals Emec final. What is the Emec initial? Emec initial is basically the EP initial plus EK initial. And we are saying that plus work done by friction should be equal to the Emec final, which is the EP plus EK final. Now, since the EK initial and the EK final are the same, they're the same, we can actually subtract them from this equation. We've got the same quantity here. So the EK initial and the EK final can disappear. Then we are left with the EP initial and the EP final. All right. So we can now say the work done by friction is equal to EP final minus EP initial. EP final minus EP initial is the same as this one, delta EP. So we come back again to work done by friction equals delta EP, which is the work done by gravity. And we'll end up with the same answer. Work done by friction is that amount. So initially, if you're going to use the work energy theorem, I advise you to draw a free body diagram, see the forces that are acting, and then you'll be able to solve this problem. Thanks for watching this video, guys. Remember, Science in 5, we are here to keep the science alive. See you next time when we discuss question 6 in this paper, the Doppler